In this series of lectures, we're going to start talking about easy problems. We've seen a lot of easy problems before, and now we're going to talk about them a little bit more formally and have a broad framework for how to discuss easy problems. For us, an easy problem is any problem where we can find an optimal solution in polynomial time. We haven't talked about polynomial time in a formal way, and we're not going to introduce it in a very formal way. We could talk about polynomial time as the running time of an algorithm in terms of the amount of bits that we encode the problem in. But talking about bits is a little bit too complicated, so instead we're going to keep it a little bit simpler. Instead, we're going to talk about the size of an instance. And the size can be anything. In the case of a graph, the size of the instance is the number of nodes and the number of edges. And for our purposes, having this rough idea of what the size of an instance is going to be sufficient. To be a polynomial time algorithm, the algorithm has to run in order n to the k time for some constant k. This is our big O notation for the running time of our algorithm, and it's important here that this is some constant k. So for example, if we have an algorithm that runs in order n to the square root of n, this is not polynomial. Any algorithm that runs in big O of n to the k time for some constant k is going to be described as a polynomial time algorithm. One of the main things that we're going to use in talking about easy problems is linear programs. We're going to use this fact that a linear program is an easy problem to solve. That is, given some linear program instance, we can solve it in polynomial time in the size of the instance. We're definitely not going to prove this fact because it's pretty challenging, but we are going to use this quite frequently. In trying to model a problem, if we can model it as a linear program, then we know that we can solve it efficiently, or that it's an easy problem. What's important to notice, though, is that when we solve a linear program, the polynomial that it runs in, its running time, depends on the number of constraints and the number of variables. Here, the set j indexes all the set of constraints, and the index I indexes all the variables. The running time to solve this linear program depends on the size of the LP. And specifically, it depends on how many constraints and how many variables there are. So, for example, if we were to model our problem as a linear program, but this linear program has an exponential number of constraints, then in fact we haven't found an algorithm or a solution techniques that's going to solve this problem in polynomial time. That's because the algorithm for the linear program is going to run in exponential time in the original problem instance. We can see how this fact about linear programs being easy to solve helps us in solving integer programs. And the connection, at least initially, is going to be through ideal formulations. Here we have some integer program, and the set of feasible points is denoted by x. Here, x is a set of lattice points. On the other hand, we also have a linear program, or the linear programming relaxation of this integer program. And here we just look at the polyhedron P. When we draw the polyhedron P, we know that we can suppose that it's an ideal formulation. And when it's an ideal formulation, that means that this polyhedron P is actually just the convex hull of the feasible points x. And we know that if we look at the objective function f of x, that the solution to our integer program and the solution to our linear program are both at the same point. This is a general feature of ideal formulations. What's interesting, though, is that if we put any other objective function here, let's suppose we have g of x, that the same thing is true. At this new objective function, the optimal value for the linear program is the same as the optimal value for the integer program. And we can do this for just one more objective function. Let's suppose this one is called L of x. And again, the same thing is true. The optimal solution, when we look at L of x as our objective function, is the same for the linear program and the integer program. What we can say then is that the optimal solution to our integer program is equal to the optimal solution to our linear program for any linear objective function. It's important here that this objective function is linear. We already sort of knew this. In an ideal formulation, the objective values of the integer program and the linear programming relaxation match each other. But now when we're talking about easy problems to solve, we can say that if we have an integer program and we have an ideal formulation for this integer program, then it's an easy problem because we can take the linear programming relaxation of this problem, we can solve this linear program in polynomial time, and then because the optimal solutions match with each other, the linear program optimal solution is actually the integer program optimal solution. In this way, ideal formulations immediately show us that we have some method to solve an integer program in polynomial time. These ideal formulations let us connect integer programs to linear programs in a very nice way, theoretically. And as a result, we can show that an integer program can be solved in polynomial time by solving the linear programming relaxation. Unfortunately, showing that a formulation is ideal is generally pretty challenging in practice. So instead, we're going to use the other objects that we've been talking about to connect integer programs to the linear programming relaxations and use them instead. Specifically, we're going to be using the integrality gap, dual bounds, primal bounds, and also talk about feasible solutions to the integer program. We're generally going to use two techniques to show that we have an optimal solution to our integer program, or to show that our integer program can be solved in polynomial time. The first technique is going to be to show that the integrality gap between our integer program and linear program is 1, or rather that there is no gap. Once we prove this, we're going to have some feasible solution to our integer program, z tilde, and we're going to show that this feasible solution is actually equal to the value of the linear program. Since this feasible solution is equal to the value of our linear program, and we know that our linear program is equal to the value of our integer program, we know that this feasible solution to our integer program is actually an optimal solution. The second technique we're going to use is we're going to construct some solution, say z tilde, and we're going to show that this solution value is at least the solution value of some dual bound. If we have a feasible solution that's at least the value of a dual bound, we also know that this feasible solution is a primal bound that is less than or equal to z tilde, or z star. And so as a result, we conclude that this feasible solution we have, z tilde, is actually equal to the optimal solution of our integer program. These are the two techniques we're going to use to show that we have an algorithm that produces a solution that's optimal to our integer program. And in general, this is how we're going to show that we can solve our integer program in polynomial time. Before we continue with the rest of the lectures, I'd like to give a little bit of an overview of how we're going to travel. First, we're going to talk about shortest path problems. Shortest paths problems are easy to solve, but we're not going to show that. Instead, we're going to talk about shortest paths, we're going to model them as integer programs, and talk maybe a little bit about how we solve them. This is really just a warm-up though. This is to get us to start thinking about how to model flow problems. We'll introduce what a flow problem is, and we'll use it as a modeling tool. Flow problems also have a lot of interesting properties that can help us solve problems. It does turn out that flow problems are easy to solve, but again, we're not going to prove it. Finally, we're going to move to totally unimodular constraint matrices. It turns out that if our integer program has a totally unimodular constraint matrix, that it actually has an ideal formulation, and so solving the linear program is equivalent to solving the integer program. This is one case where having an ideal formulation is really easy to identify. When talking about totally unimodular constraint matrices, this is the most general form we'll be talking in. We'll use totally unimodular matrices as a modeling tool, but also we're going to start proving things. We'll prove why, when we have a totally unimodular constraint matrix, the linear program is identical to the integer program. We're also going to show that all of the previous problems we talked about, the shortest path problem and the flow problem, fall under a totally unimodular constraint matrix. The way we should think about this is that we're going to slowly move towards more generality, and when we finally get to the most general case, we're going to start proving that all these problems are easy to solve. Along the way, we're going to introduce two other specific problems that happen to be useful as modeling tools.